नमस्ते बच्चों, हमेशा खुश रहो। माई सेल्फ जीवी डॉक्टर मोनिका त्रिवेदी, डिपार्टमेंट ऑफ साइंस एंड टेक्नोलॉजी, फैकल्टी ऑफ एजुकेशन एंड मेथोडोलॉजी, ज्योति विद्यापीठ, वुमेन्स यूनिवर्सिटी, Jaipur. So students, today's topic is dyes and their classification and their color constitution. So the color of a dye is related to the Wet's theory, which is given in 1876. According to this theory, the dye is made up of two essential kind of part. One is a chromophores and another is a oxychromes. Okay, according to him. He produced that the color produced he stated that the color produced by the dye because of the chromophore, and this chromophores comes from the Greek word chroma, which means the color, and phore means to a carrier. Okay, the chromophores are an unsaturated group present of at least one of such group is essential to produce a color in a aromatic in a organic compound, and a molecule containing such a group are called as a chromosomes. So there are some example of chromophores or chromosomes. Okay, thus for the example, the nitrobenzene is a pale green color, azobenzene is orange red color, p quinones are yellow, and the o quinones are orange or a red color. Okay, containing other unsaturated groups produce the color only when the several of them are present in a molecular and when they are conjugated. Thus, through the acetone is colorless, and by acyl is a yellow in a color. Okay, so there are some oxychromes which are present with the chromosome, and they are not directly associated with the color, and they do not produce color themselves. Okay, but they are able to intensify the color when they present with the chromophores. Okay, like OR, OH, NH2, NHR, and NR2 groups are oxychromes. Okay, so the next theory is modern theory of the color. According to this theory, when the light falls on the substance, light may be completely reflected. In this case, the substance will appear white, and if it completely absorbed, the substance will appear black. If a substance absorbs all the visible light except the corresponding light, for example yellow, it will transmit or reflect only yellow color, and we will be seeing a yellow color. However, it is generally seen that the yellow of all the one color is absorbed, in which case the substance will appear to have the complementary color. Thus, if the light is absorbed from the violet region of a spectrum, the substance will be seen as yellow in a color. If a light is absorbed from the red region, the substance will be appear in a green color. So here are the complementary colors of original color which are absorbed by the surface of the substance. Next theory is a valence bond theory. According to this theory, it is the resonance stabilization of an excited state that is responsible for the absorption of a visible region. When an ultraviolet or a visible light is absorbed by the molecule, an electron is excited. That is, it is promoted to an orbital to the higher energy. The wavelength of a light absorbed depend on the energy difference between the excited and the ground state of a molecule. The smaller difference between the two states, the longer is the wavelength of a good absorption. The energy required to promote an electron depend upon the environment of an electron. Like for a sigma bond, electron are firmly held and very high energy, or a short wavelength. It is necessary to promote electron and may at the time break the molecule and form the free radical. The pi electrons are less firmly held and require less energy or longer wavelength to excite it. Electrons belonging to the conjugated system require even less energy because they have still longer length. The conjugation and the resonance stabilize the excited state by the sharing the delocalization higher energy of excited electron. The conjugation and resonance increases the wavelength of the light absorbed or also increase, and when the wavelength is longer enough to be in the visible region, we can observe the color. The colorless compound. This is alkene, which is it is a colorless compound absorbed at 1800 angstrom. You can see here the alkene, also diene. This is the diene, and this is also colorless and absorb at 8170. Okay. This is also the these compounds show the conjugation and resonating structure, and these are colorless. The next theory is molecular orbital theory. According to this theory, the electronic transition can occur by the absorption, okay, and of ultraviolet and the visible region. Although the transition are the possible only the followed by the n to sigma star, n to pi star, and pi to pi star. A sigma to sigma star transition takes place when the bonding of a sigma bond electron is excited to the its anti-bonding sigma orbital, and that is that the sigma star. This type of transition require a very large amount of energy, as the sigma electron are very tightly bonded. Hence the compound like saturated hydrocarbons which do not have any pi or sigma electron may undergo only the sigma to sigma star transition. However, this transition do not take place by absorbing in the ordinary ultraviolet region. Okay, this is the transition allowed for the molecular orbital theory. Now, what are the dyes? If you know about, the dyes are a colored organic component that are used to impart the color to the various substances, including paper, leather, fur, hair, drugs, cosmetic, waxes. They plastic, textile industries material. So these are some materials which are colored, which shows the color. So dye molecule is a colored compound normally used in a solution which is capable of being fixed to a fabric. Okay, to be used, dye must possess the following four properties. First is a color, second is a stability in a water, ability to absorb and retain by the fabric, okay, to be chemically combined with it. The fourth one is the ability to withstand washing, dry cleaning, and exposed to the light. The dye has a color due to the presence of the chromophore and its fixed property to the acid or a basic group such as OH, SO3H, NH2, and R2, etc. The polar exochrome make a dye water soluble and binds the dye to the fabric by interaction with the oppositely charged group of a fabric structure. Now, the classification of dye. The dyes are classified on the basis of the source material. Okay, so first is the natural dyes are dyes or a color derivatives from the plants, from the invertebrates or mammals. A measure of the natural dyes are a vegetable dye like plant sources, from the plant sources like root, berries, bars, leaves, and wood. Okay, the other organic sources include the fungi and leeches are also the natural dye. The second one is a synthetic dye. Almost all the color that you can see today are synthetic dyes. Some the synthetic dyes are used everywhere in the everything, from the clothes to the paper to the from the food, from the wood. Okay? This is because they are cheaper to produce, and they are brighter, they are more color fast, and they easy to appear on to the fabric. Next, the classification on the basis of the chemical structure. The first one is a nitro dye. Nitro dye are a polynitro derivative of phenols containing at least one of the nitro group or ortho or para to the hydroxyl group. They are little importance in on the behalf of the industrial use because the color is not very fast. So, and this is the structure of a nitro dyes versus the picric acid and naphthol yellow S. The naphthol yellow S can be used to dye the wool and is one of the color permanent in foods. The azo dyes are by the far the most important class. According for over 50% of all commercial dyes, they are characterized by the presence of one or more azo groups and double bond N group, which form the bridge between two or more aromatics ring. This is the dimerization process to make the azo dye. Here you can see NaNO2 plus HCl give the HNO2 plus NaCl, and this HNO2, the nitrous acid combined with the aromatic ring, aromatic amine, and it will give the diazonium compound. Okay, and this will further go in a coupling reaction, and it will give the azo dye. Next is aniline yellow. Aniline yellow, here the preparation method of aniline yellow. The aniline yellow is used as a dye for oils, and it is a very intermediate dyes for the other dye preparation. Next is the butter yellow. Butter yellow has been used for the coloring of butter and oils. Okay, next is Carsodian is a orange red dye. It is used for a dyeing purpose, leather and jutes. Okay, these are the synthesis reaction for the dyes. Next is a methyl orange, and there is a methyl orange dye is prepared from the diazotization of sulfonic and N-dimethyl The first product obtained from the coupling is bright red acid from the methyl orange, and it is called as a helenthine. Okay, this is the structure of helenthine, and in this base helenthine is converted to the orange sodium salt, which is called as methyl orange. Okay. You can see the diazotized sulfonic acid converts into N-dimethyl and it will undergo and it will give the helenthine, and this helenthine converts into the methyl orange dye. The methyl orange is a pH indicator, and it is clear that the color change it's very often used in a titration. Methyl orange changes color at the pH of a mild strength and acid, and it is usually used in a titration for the acid. Unlike a so-called universe indicator, methyl orange does not have a full spectrum of a color, but it changes the color. Okay. This is the powder of the methyl orange, you can see here, and this is the left methyl orange in an acidic solution and right methyl orange in a basic solution. So it varies the color from the acidic and basic solution. The methyl orange is often used as an acid-base indicator in the solution that are more base than the pH 4.4. Methyl orange exists almost the yellow negative ion in a solution that are more acidic than the pH 3.2. It is prominent to form a red dipole ion. Here you can see it will give the ions of in a acidic medium. Now the next is Bismarck brown. Bismarck brown, it is also a diazo dye. The Bismarck brown is observed by the coupling tetraazotazides M-phenyl and dimethylene with the 2 moles of M-phenyl and diamine. Okay, so this Bismarck brown is used for dyeing the leather, wool, and cotton. This is the preparation method, and it will prepared by the coupling reaction of phenyl and diamine and the tetraazotized phenyl and diamine, and it will give the Bismarck brown. Now next is a diphenyl methylene dye. Diphenyl methylene dye. This is the skeleton of diphenyl methylene dye, and there is an example of Oramine O. This is the structure of Oramine O is used for dye the wool, silk, nylon, rayon, and paper. Next is a triphenyl methyl dye. Triphenyl methyl dye have a central carbon atom is jointed to the 2 benzene ring, and the p quinonoid group. Okay, like malachite green. This is the structure of a malachite green. The triphenyl, you can see the triphenyl ring here in their skeleton. So the triphenyl methylene dye are not fast to light or washing, however, except when applied to the acrylic fabric. They are used in a large quantities for coloring the paper and the typewriting ribbons, where the fastness to the light is not so important. Next is the xanthine dye. Xanthine, this is the structure of a xanthine dye, the three phenyl ring over here. The xanthine dye, the fluorescence is one of the valuable dyes, and it is a red powder which is insoluble in water. The sodium salt of a ferrocene is called as a uranium, and it is used as a dye for a wool and a silk. This is the synthesis method for a fluorescence to the urine. Now next is a thelanine. Thelanine is a phenolphthalein dye, and the phenolphthalein dye is not a dye. It is a colorless solid which have a melting point 261 degrees centigrade, and it's insoluble in a water but dissolved in alkaline to form a deep red solution. Because of the color change shown above, the phenolphthalein is used as an indicator in acid and base titration. The phenolphthalein is extremely powerful dye which is used in a laboratory. Okay, and this is the synthesis of phenolphthalein, and which is converted into the sodium salt, and it will give the trisodium salt, which is a colorless. So this is the reaction of acid base titration. The phenolphthalein changes into the sodium salt, which is red in color, and then the colorless in a solution. The next is the indigo dye. Indigo dye is an aromatic compound with disactivated blue color, and the indigo was a natural dye extracted from the plant, but today nearly all the indigo dyes are produced synthetically. This is the structure of indigo dye. The primary use of the indigo is as a dye for a cotton, and it is mainly from the production of the denim cloth for a blue jeans. A small amount are used for the dyeing for a wool and a silk also. Anthraquinone dyes any of the group of the organic dyes having a molecular structure based upon the anthraquinone. Okay, like alizarin. Alizarin is an anthraquinone dye. It has an anthraquinone group here. So the alizarin is used as a commercially as a red textile dye. Now the classification based on the method of this application. According to application, the first is a direct dye. They carried out in a natural or a slightly alkaline dye solution. It contains acidic or basidic oxochromes. They are polar in nature, used for cotton, paper, leather, wool, silk, and nylon. This is the structure like Amartya's yellow is direct dye which is combined with the fabric, and it will show the color. It has a acidic oxochrome here. The second is a mordant dye. This class of dyes require a permanent of the fabric with the mordant material designed to bind the dye. A mordant is any substance which can be fixed the fabric and react with the dye to produce a color on a fabric. Actually, the mordant form a insoluble coordinate compound between the fabric and the dye, and the bound with the two. The malachite mordant like a salt, aluminium, chromium, iron, tin, etc., which are used with the acidic dye. The alizarin is a classical mordant dye. It provides different color depending on their mordant. It gives a red color with aluminium, tin, and tin salt, a brownish red color with the chromium mordant, and a black violet with an iron mordant. The two type of bonds are involved in a fundamental reaction between a mordant dye and a mordant. One is a covalent bond with usually hydroxyl or oxygen and the metal bond. Another is a coordination bond with a metal with the double bonded with the oxygen. This is the structure of a malachite dye, the alizarin dye. and here you can see that the alizarin dye here with the presence of L3 and fabric, it will bind with the L3 and it will give the red color for the fabric. Next is a wet dye. These dye are insoluble in a water, but on the reduction with the sodium hydrosulfide yield the alkaline soluble form and the leuco compound, which may be colorless. It is in this form they are introduced into the fabric. After the reduced dye has been absorbed in the fabric, the organic insoluble colored dye is reformed by the oxidation with the air or a chemical. The wet dyes are used to dye cotton and are very fast because they are insoluble in water. So indigo is a good example of a wet dye. Here you can see blue and blue water insoluble indigo. By the oxidation and reduction, it will give the colorless water soluble compound indigo, the leuco-based compound. The next is ingrained dye. These are also called as a developed dye. These dye are actually made up inside the fabric of fibers of a fabric, and this fabric is treated with the two compound used as a synthesis for the dye. These precursors molecule are small enough to diffuse into the pores and space between the fibers in the fabric. Then they react to form a dye which is trapped inside or into a grain to a fabric. Because of the large size of the dye molecule, azo such as prepared are used as ingrained dyes for the cotton. The fabric is soaked first in a solution for the coupling compound beta naphthol, and then in a solution of diazotized p-nitroaniline. Next is the dispersed dye. These dyes are insoluble in water but are capable of dissolving certain synthetic fabrics. Dispersed dye are usually applied in the form of the dispersion of finely divided dye into in a soap solution in the presence of some soluble agent such as phenol, cresol, and benzoic acid. The absorption in the fabric is carried out at the high temperature and pressure. The dispersion dyes are used to dye the acetate, rayon, nylon, and other synthetic fabric. Okay, so the silicone first pink B and the silicone first blue B are the example of the dispersed dye. This is the this is the structure of silicone fast pink B and the silicone fast B blue B. Okay, so the dispersion dyes are a ready-made dye and are insoluble in water and or heavy. They have very low water solubility. They are organic coloring substance which are suitable for dyeing the hydrophilic hydrophobic fiber, and dispersed dye are non-ionic dye, so they are free from the ionization group. Dispersed dye are used for dyeing the man-made cellulose ester and the synthesized fabric, especially acetate and the polyester fibers, and sometime nylon and acrylic fabrics. They are carrier for the dispersing agent are required for the dyeing with the dispersed dye. The dispersed dye have fair to good light fastness with rating about 4 to 5. Thank you very much.